All right, we're back with the practice set from 1.3. So we are on page 29 right now. We're going to go ahead and go 15 through 21. So number 15, a phone company offers a monthly cellular phone plan for $25. So basically, when you sign up for this monthly phone plan, you're paying a flat rate of 25 bucks. The plan includes 250 anytime minutes. So basically, no restrictions. You just use 250 minutes whenever you want, and charges 20 cents per minute above 250 minutes. So basically, if you use anywhere between 0 minutes and 250 minutes, you're just paying 25 bucks. But once you use 251 minutes, you're going to start paying 20 cents per minute above that given time frame of 250 minutes. Write a piecewise function for C of x. So they're telling you they want you to label it C of x, so we will. The cost for using X minutes a month. All right, so number 15. They want to use C of x. Since this is a piecewise function, we know we're going to have at least two parts to it, maybe more, but I'm pretty sure there's only kind of two rules here. One where you pay the $25 and you use up to and including 250 minutes. And the other one where you use more. So I think we're just going to have two equations here. The first one says $25. That's the cost from 0 to 250 minutes. It's 25 bucks. No hidden fees, no surprises, no nothing like that. So I think our first equation is just going to be 25 bucks, just a 25. Pretty straightforward. So our domain restriction, though, remember there's a caveat. As long as you use anywhere from 0 to 250 minutes. Make sure you're watching your signs. Can I use 0 minutes of a plan? Sure. I can go to Verizon, buy a plan, and not use it at all. But guess what? I'm still going to pay that $25 a month. So 0 is included. Make sure you read your problem correctly. Am I including 250 minutes? Yep. If you go and read through that, the plan includes 250 anytime minutes and charges 20 cents per minute above 250. So that $25 is good all the way from not using it at all to 250 minutes on the dot. The next equation is going to take into account talking over 250 minutes. So if I look at this equation, if I talk over 250 minutes, I'm already going to pay that $25 original plan fee, right? I've already paid that. I'm above and beyond that. So I need to make sure I include that in my equation because I've already paid that. This 20 cents that I'm paying per minute goes on top of that. So I think my slope then is going to be 0.2x, and then 0.2x plus 25 would be my equation. $25 for the plan, and then 20 cents for every minute on top of that. Remember, there's a restriction or there's a domain, there's a caveat here. Anything above 250 minutes. So I'd want to state that as long as x is greater than 250 minutes. Number 16, graph this piecewise function, state domain and range, identify whether the function's increasing, constant, or decreasing. Okay, so I think with this one, I'm going to need a piece of graph paper. Let's do this. Okay, I'll cover that problem up here in just a second. I want to make sure I got it right. So I'm graphing those three functions on this coordinate plane. So all three functions are all going on the same coordinate plane. So if you don't remember from Algebra 1 how to graph a line, all these are linear functions, make sure you Google that, right? There's basically two steps. Plot your y-intercept and apply your slope, okay? So my first line, positive 3. So I'm going to have a y-intercept at positive 3, and then my slope is 1/4. Remember, slope is rise over run. My up and down over my left and right. So I'm going to go up 1 over 4. Up 1 over 4. So let me do my best to draw this line for you. And there's a reason I'm drawing it pretty faint, because I don't want all of this line, right? I only want a piece of it. If you look at your problem, I only want the piece of this equation that goes from -2 up to 0. Everything else I can erase, I can forget about. So the only piece I want to keep from this equation goes from x equals -2 to x equals 0. So let's go focus on that. There's -2, there's 0. So anything outside of that, I can erase, and I think I will. To me, obviously some people maybe that are just way smarter than me can sit there and visualize that, and you know what I mean? They can just draw that little tiny segment. For me, I've got to use pencil, and I just can't do that. So I've got to draw my line, sketch it, and then just erase what I don't need. So from -2 to 0. Remember, your endpoints are going to be dictated by these inequality signs. So since this is a strictly less than sign, that means that point is going to be open. Since this is less than or equal to, that means that point is going to be closed. All right, keep going. 2. So basically y equals 2. If you don't remember, y equals 2 is basically going to be a flat line. So a flat line that doesn't have any slope at all, just a flat line. But I only want to go from 0 to 4. So from 0 to 4, so from here to here, I'm going to draw that line, y equals 2. And I always push you guys to use rulers, so I'm going to do the same thing. I'm going to practice what I preach. So 0 to 4. 0 to 4. All right. And again, those inequality signs will tell me what an open circle or closed circle. So that's strictly less than, so that should be an open circle. That's less than or equal to, so that should be a closed circle. And then the last piece, 3 minus x, or I like to think about it like this, -x plus 3. I just like to have it in that order. So I know my y-intercept is +3. Bam, I've already got a point there. And I know my slope is -1. So it's basically going to be a downhill slope that goes through that y-intercept of +3. But keep in mind, right, this only exists between 4 and 7. I'm going to go ahead and just sketch that out, though. If my y-intercept is at +3 and my slope is -1, that means from that y-intercept, I'm going to go down 1 over 1. Bam, there would be a point. Down 1 over 1. Down 1 over 1. Down 1 over 1, right? That gives me my line. So let me do my best to draw this. Okay. And again, this function only exists between 4 and 7. My x value is between 4 and 7. So I want to basically erase everything outside of that. So I'm going to erase everything to the right, everything to the left. Don't be digging too hard in with this pencil, because otherwise you won't really be able to erase that. It'll be kind of still visible. At 4, it's going to be strictly less than, so that's going to be an open circle. At 7, it's going to be a closed circle because it's less than or equal to. So there is that picture. There's my first equation. There's my second. There's my third. One thing I really want to point out that I'm sure you already know, notice that these equations technically overlap. Well, I should say they look like they overlap, but technically they don't. Whenever they hit the same point, the same the same x value of 0, notice one is filled in, one is not. Same thing with x equals 4. One is filled in, one is not. You can't have x equals 4 and have two filled in circles at x equals 4 or at x equals 0. It wouldn't be a function then. So just notice that, like when they're stacked on top of each other like that, one should be filled in, one shouldn't be. I think it was asking us some extra stuff in there. State the domain and range. So for this first equation, I'm going to go ahead and do it like this. For this first equation, my domain is right there. They give it to me. It's in the piecewise function. So there's my domain. If you want to use, set notation or whatever, you're more than welcome to. It goes from -2 to 0. It's not including -2, and it is including 0, right? Strictly less than or equal to. So it would look something like this. So there's my domain, and then my range for that first equation. If you look at it, it looks like it just lives from... That looks like it's at 2.5. I believe the slope was 1/4. So down 1 over 4. So down 1/2 over 2. So that's 1/2, or I'm sorry, that's 1/2. Yeah, down 1 over 2. So my slope there, or I'm sorry, my my range, sorry, I'm getting twisted up, is at 2.5 all the way up to 3. Notice at 2.5, it's an open circle, so we don't want to include that. But at 3, it is a closed circle, so we do want to include that. So there's my range for the first equation. The second equation, 2. Again, domain's listed there. My range, it's only 2, right? It doesn't go above 2. It doesn't go below it. It doesn't exist outside of y equals 2. So I would just say that, y equals 2. And then my third equation, there's my domain. You can visibly look at it. It looks like it exists from -4, including -4, right? It's closed, all the way up to, but not including -1. So for my third equation, it goes from -4 all the way up to, but not including -1. So remember, domain is the width of your function. Range is the height of your function. Identify whether the function's increasing, constant, or decreasing. You can see that this first function is going uphill, so that's increasing. You can see that the second function is flat, so that's neither, it's constant. And you can see the third function is going downhill, so that's decreasing. All right. 17, write the rule that defines the function for the following graph. It looks like we got 2 equations there, right? So this is a piecewise function with 2 separate equations. So for number 17, one of the 2 equations, it doesn't tell us what to name it, so you can call it whatever you want. It doesn't matter. I mean, f of x is my go-to, so that's what I'll use. Again, we see 2 lines, so we know it's 2 separate equations. Doesn't really matter which one you put first. We'll go ahead and put the one on the left first. It looks like this slope here, if I go find one point, it looks like it's going up 1 over 1. Up 1 over 1, up 1 over 1, right? So it looks like it's increasing up 1 over 1 each time. So if I kept going, it would cross my y-axis right there at 5. So I know my y-intercept is 5. And again, I already said that the slope, up 1 over 1, up 1 over 1, is just 1. So I think that first equation is going to be x plus 5. And it looks like the second equation is just a flat line. And it's a flat line at y equals -2. So the first equation looks like it's an arrow that goes down into the left forever. So my restriction here, my range here, is going to be from -1 to -infinity, right? At -1, that exists because it's a closed circle. So I want to include that point. And since this goes down into the left forever, more importantly, the left forever, it's going to go towards -infinity. So my restriction here is going to be -1 is, actually, I'm going to rewrite that. Let's change that. I'm just going to kind of pen this in. So excuse my, nope, that's going to bug me. Sorry. I gotta redo it. I gotta white it out. There we go. Nothing but the best for you guys. -infinity, you always want to start with the lowest value, right? Like here, 0 is less than x, which is less than 250, less than or equal to. So -infinity is definitely less than -1. So -infinity is less than x, which is less than or equal to -1. Don't forget, anytime you're referencing -infinity as a domain or a range, you can never include it. So it's always less than or greater than. -1 is included because it is a solid circle. Then with my other function, it looks like it goes from 1 and it goes right forever. It never stops going right. It's not going to include 1 though, because it's an open circle. So it's going to be 1 is less than x, which is less than infinity. Let's make sure that that's all I needed. Write the rule. Yep. So that's good to go. Number 18, right? Each absolute value function is a piecewise defined function. So I'm going to start off with showing you the easy way with number 18. And then with number 19, I'll show you the hard way. And you can choose whichever way you would like to do that. So let me share my screen here. If you look at number 18, it's f of x equals the absolute value of 3x plus 1. You'll notice that I have that graphed right here. That's the red line. You can always see which equation I'm talking about because this is red and my graph is red. This Desmos program, just to give everybody a heads up, Desmos is located, it's embedded inside of Envision. It's under your math tools. But if you don't know where it's at, that's cool. Just search Desmos. And then on Desmos at the top, there's a drop-down screen or a drop-down menu for math tools. Just click on graphing calculator. And this will pop up. Super useful. Some people have been asking, can I use this all the time? Of course, definitely. I think to me, visually looking at something kind of tells more of a story than reading something on paper. So here's my equation. They want me to write an absolute value, a piecewise function for this. One thing I really want to emphasize visually looking at this function is that an absolute value function is basically this. It's y equals 3x plus 1, right? But the difference between number 1 and number 2, the red and the blue function here, the blue function is just a linear function. It's a straight line. But the red function takes everything below that x-axis and bounces it back up because of this absolute value grouping symbol, right? Absolute value, you can plug negatives into it, right? So if x equals -1, I can do that. But if I do the math inside of my grouping symbols and I get y equals the absolute value of -10, well, then it automatically is going to output the positive version of that number, always. The output to an absolute value equation is always a positive number. Whatever you're pulling out from that inside those grouping symbols is always positive. So it makes sense. If I have this equation, well, I can't have this stuff down below the x-axis because all these y values are negative. I can't do a bunch of math inside of an absolute value function and get negative answers. It just doesn't work. So what I need to do is show that. So everything like from this original blue line that you could see there, all this stuff from below the x-axis just got reflected and bounced back up. So you could see if I add that blue line, the blue line represents one side of that equation, the green line represents the other. And I'm sorry, I have to go let my dog out to go pee before she goes on the rug. So I'll be right back. I'm so sorry. Okay, so looking at this absolute value function, what's happening here is you have these two equations. There's the blue one, I'm pinging on and off, and then there's the green one, I'm turning on and off. You can see that basically these two functions, this blue and this green one, represent the absolute value function, right? So these are the two functions that I'm going to use. Notice it's y equals the absolute value of 3x plus 1. So both of those numbers are positive in one of my equations, and both of those numbers are negative in my other equation. That's just the way it works. Okay? So I've got my piecewise function right there. It's as easy as that. So let me go back over to my video. And let's write this down. So for number 18, f of x equals the absolute value of 3x plus 1. I'm going to just call this a of x. I don't think it really matters what you call it because they're not telling you to name it something specific. And again, one of my function was absolute value of 3x plus 1. So like we said, one of them is going to be the positive of both of those numbers, and one of them is going to be the negative of both of those numbers. Okay. To find the domain, we're going to go back to our graph, and let me show you. So I'm going to hide these and go back up to my absolute value function. One cool thing about Desmos is it's pretty interactive. I can go down here and I can click on that vertex, and it'll tell me exactly what that location is for that vertex, the point value is. So I'm going to call that negative 1/3 instead of that, because that sounds exhausting to read that. So negative 1/3 comma 0. That's that tipping point. So from this point left and from this point right, those are my two equations, right? This point left and this point right. Those are the two separate equations, negative 1/3 comma 0. So let's go back over to our problem. Negative 3x minus 1 is the part that goes like that. And then, watch out, I'm going to get super fancy on you. That one is the part that is that one. How do I know that? Well, if those are my two equations, this is a negative slope, so this should be going downhill, right? That matches. This is a positive slope, so that should be going uphill. That's how I know that. So if this vertex is at negative 1/3 comma 0, I can create my domain for each of those. So let's talk about the black function first. It looks like it exists everywhere to the left of negative 1/3. So for my black function, it's going to be negative infinity is less than x, which is less than negative 1/3. And then the second equation, which is my top one, the blue one, 3x plus 1. And since I used a separate color, I'll use the separate color here. It's going to be, it looks like it goes from my vertex, negative 1/3 to the right forever. So we'll call it negative 1/3 is less than x, which is less than infinity. All right. So 19. This is the one we're going to kind of do the long way. So buckle in. If you want to skip over 19, type that in that Desmos calculator and use it that way. I would if I were you. But let's just look at this the long way, just for fun. 19. G of x equals absolute value of negative 2x minus 6. Okay. So there's my function. The first thing I need to do is find that vertex. Remember, we were just kind of referencing that. That vertex is where that function splits. That absolute value function is going to split at that point. So we want to find what that vertex is. So what we need to do is solve this. So what I would do, and I want to start using some color because it's kind of fun, is just say, figure out what that is. Instead of g of x, I could just plug in 0. If you don't remember, solving for x-intercepts, that's what essentially we're doing. It's always equal to 0. Your equation's always equal to 0. So if I solve this, I'll add 6 to both sides. Divide both sides by negative 2. And I get x equals negative 3. So I know my vertex is at negative 3. See, why do I do that? Negative 3 comma 0. Negative 3. Oh, now I'm messing it all up. There we go. Negative 3 comma 0. That's my vertex. That's that splitting point, right? Where the left side meets the right side. Now that I have the vertex, what I have to do is basically calculate the line. So what I want to do, if I have this as an absolute value function, I found that. What I want to do is find a point to the left of it, and that's going to help me find this line. And then I want to find a point to the right of it, which is going to help me find the second line. Pick a point. It doesn't matter what you pick. You could pick negative 10, negative 100. You can pick any value you want, just for the sake of, just ease. I'm just going to pick a nice even number like negative 4. So if I choose negative 4, let's plug that into our function, negative 2x minus 6. So it's going to be negative 2 times negative 4 minus 6, which is negative 2 times negative 4 is 8. 8 minus 6 is 2. So that gives me the point negative 4 comma 2. All right. So now that I have a point and I have my vertex, I can find the point for the other side. So again, this is the side that's this one right here. We'll draw it with green. My other line, how do I know that? And again, because I use this equation, negative 2x, so that's a negative slope. So the second equation is going to be the positive slope. So it's going to be, instead of negative 2x minus 6, what I'm going to use is positive 2x plus 6. So pick a point to the right of that vertex. That vertex, again, is at negative 3. You could pick 0. You could pick whatever you want. I'm going to pick 0 because I think it's going to help me out. So that's going to be, I didn't want to write 0 here, so ignore that, please. 2 times 0 is 0. 0 plus 6 is 6. So that's going to give me the point 0 comma 6. So Again, I apologize. Let me go let my dog in. Okay, again, I'm sorry. So what I did was I took this absolute value function, I split it up into two lines, the green line and the orange line. The green line I know is going to have a vertex, or it's going to stop at -3, 0, because that's my vertex. So all I had to do was find a point to the left of that vertex. Well, now that I have a point here to the left of the vertex along with the vertex, I can figure out what the equation is. Same thing with the right. I can figure out the equation of the orange graph as long as I have one point, that's the vertex, and then another point on the other side, on the right side of the vertex. So that's what I'm going to do now. So let's take care of the green line first. We know that that is that is going to have these 2 points, the vertex, and then the green point. So what I need to do is calculate the slope. So remember, slope is the change in y over the change in x. So it's going to be subtracting your two y values and then divided by subtracting your two x values. My numerator is 2. -4 minus -3 is -1. So I know my slope is going to be -2. Okay. Now that I know my slope, I can plug that into my equation. Remember, it's always y equals mx plus b plus b. Right now, I know my m. And then what I can do is use one of those 2 points. It doesn't matter which one. I'll go ahead and use the green point, -4, 2, to plug in for x and y, and then I can find out what my b is. In this case, x is -4, y is 2. So it's going to be 2 equals -2 times -4 plus b. 2 equals 8 plus b. Subtract 8 from both sides, and I get -6 equals b. So I know that that green equation is going to be y equals, again, slope is -2, and my y-intercept is -6. I do that same exact process for the orange equation. I've already got my 2 points, my vertex, and then 0, 6. So what I would do is find my slope for those 2 points. Once I found my slope, I would plug it into y equals mx plus b. Plug in your slope, plug in either one of these points. It really doesn't matter. I'd just go ahead and use the orange one, 0 and 6, and then calculate that y-intercept, and then you're good to go. Once I do that, the other equation is going to be y equals 2x plus 6. So let's go ahead and put all this together. You could see why I would prefer using a graphing calculator, right? Because this can get pretty time consuming, things like that. So use the tools that they give you, right? Use a graphing calculator. Nothing wrong with that. So for number 19, I believe we said, let's call it a of x. One of our equations, the other one. And then let's see what's happening here. Again, -2x minus 6 is the part that's coming down to your vertex, right? -2x minus 6. The part that's going back up is +2x plus 6. So this domain restriction for -2x minus 6 looks like it's from that vertex, which we found, right? The vertex is at -3. So it's from -3, and it looks like it goes left forever. So negative infinity is less than x, which is less than negative 3. Then the second one, again, from negative 3 to the right. So it's negative 3 is less than x, which is less than infinity. Something I don't think I mentioned back in the last example, with 19, it doesn't really matter where you put the or equal to here with negative 3. You could put it with either one, you know. I guess you could just throw it with this one. Negative 3 is less than or equal to x. You do want to make sure that that negative 3 is included in one of those two equations. Doesn't matter which one. It's up to you. Both are correct. All right, so that's a super long answer, but that's it. 20, graph each step function. So these should go a little bit quicker. So let's take a look at these step functions. These are kind of pretty easy to do. They literally just sound exactly like what their name is. They're stepping. So for number 20, I've got that function. It looks like it's a line at y equals 2, a line at 5, a line at 8, and a line at 9. And then they're only going to exist inside of those domain values. So let me see if I can get this a better picture for you. Okay. So y equals 2. I'm going to go ahead and draw that line. Y equals 2. There's my line y equals 2. But again, remember, y equals 2, but it only exists between the x values of negative 3 and 1. Specifically, a closed circle at negative 3 and an open circle at 1. So a closed circle at negative 3 and an open circle at 1. I'm going to go ahead and erase everything outside of that. There's my first step. Y equals 5. And that goes from 1 to 4. So y equals 5 from 1 to 4. Y equals 5 from 1 to 4. 1, it's going to be a closed circle. 4, it's going to be an open circle. So at 1, it's going to be closed. And at 4, it's going to be open. Make it obvious like that if you're doing that, closed and open. Third line, 8 from 4 to 6. So 8 from 4 all the way up to 6. And at 4, it's closed. At 6, it's open. It's closed because it's less than or equal to. It's open because it's strictly less than. And then the last one, 9, from 6 to 10. Closed at 6, open at 10. So 9 from 6 to 10. Closed at 6, open at 10. And that's it. Not too bad. So piecewise function, literally just pieces of a function.